Have you ever just stared at a glass of water and thought about the sheer, untapped engineering potential sitting right there in front of you? Well, welcome to this explainer. Today we are going to completely rewire how you think about fluid power. We're taking a wild journey from the absolute bedrock of 17th century physics all the way out to the frontiers of space exploration, smart materials, and extreme quantum-level engineering. Trust me, by the time we wrap up, you will literally never look at a liquid the same way again. Here's our roadmap for this explainer. First up, we'll hit Pascal's law. Then, phase change space actuators. Third is smart damping with MR fluids. Fourth, we'll explore the hydraulophone and absement. Fifth, supercritical CO2 microstructures. And we'll bring it all home with liquid gallium synchrotron cooling. Let's get into it. Section 1. The power of Pascal's law, or as I like to call it, the baseline of normal. Okay, so to truly appreciate the bizarre extremes of fluid dynamics we're going to cover today, we first have to establish our baseline. The absolutely crucial takeaway of Pascal's law is that liquids, like oil or water, are basically incompressible for everyday engineering. You just can't squish them into a smaller volume. Because of that, any energy you put into a sealed fluid system has to be transmitted instantly, equally, and totally undiminished everywhere inside that system. And this rule gives us the absolute magic of traditional hydraulics: force multiplication. Just picture a sealed U-shaped tube. If you push down with exactly 1 pound of force on a 1 square inch piston, you create a very specific pressure. Because the fluid won't compress, that exact same pressure travels everywhere. So if your output piston on the other side is, say, 10 square inches, that pressure pushes up on every single one of those inches. Suddenly, your 1 pound of effort is lifting a 10-pound weight. You're trading distance for power, creating this massive mechanical advantage that literally drives modern industry. Moving right along to Section 2, phase change space actuators. We're talking actuation without electricity. Let's leave those heavy, active industrial lifts down here on Earth and head up to space. Out in the harsh vacuum, like on the lunar surface where temperatures are just swinging wildly, standard electronics can easily fail, and metal parts can literally cold weld together. No good. That's where phase change materials, or PCMs, swoop in as autonomous lifesavers. These are materials like certain paraffins that expand massively when they melt. Because they react directly to ambient heat, they don't need a single drop of external electrical power. Plus, for spacecraft where every single gram is strictly accounted for, PCMs pack the absolute highest energy density of any actuator type out there. This isn't just some theory either. We actually use this step-by-step process to build fully autonomous solar tracking loops. Picture a small cylinder packed with PCM. The sun beats down on it, it warms up, and the PCM melts. That fluid expands with such incredible mechanical force that it physically pushes and rotates the solar panel array to directly face the sun. Once it turns far enough that the cylinder dips back into shadow, it cools down. The fluid solidifies, contracts, and the whole panel stops right where it needs to be. It's a completely self-correcting mechanical loop driven entirely by temperature. Section 3. Smart damping with MR fluids. Magnetic solidification. So we just saw how temperature can change a fluid's volume, right? But what if you could change a fluid's actual physical state entirely on command? Magnetorheological, or MR smart fluids, can do exactly that. They flip from a smooth liquid to a rigid solid in mere milliseconds. It all comes down to a very precise chemical cocktail. You start with an inert carrier fluid, usually silicone oil, because it handles temperature well. Then, you suspend micron-sized ferromagnetic particles inside it, specifically carbonyl iron, since it's perfectly spherical and highly magnetic. Throw in some additives so it doesn't clump, and normally it just flows like thick oil. But the second you hit it with a magnetic field, those iron particles instantly snap into highly structured chains. When you break down the physical engineering of a smart actuator, it's pretty brilliant. You have a bobbin and a flux return inside the valve. Run an electrical current through the wire coiled around that bobbin, and boom, you generate a magnetic field across the gap. The fluid flowing through instantly reacts, locking into a semi-solid state known as a Bingham plastic plug. You are literally creating a solid physical blockage out of a thin fluid. This gives engineers real-time, variable control over damping and vibration, which is an absolute game changer for everything from high-tech prosthetic limbs to earthquake-resistant skyscrapers. All right, Section 4, the hydrophone and absmeasement, the math of expression. We are definitely escalating the weirdness now. We're stepping away from traditional actuation to completely redefine the fluid user interface by mixing fluid dynamics with musical computation. Yeah, you heard me right. It brings up this really profound question. How exactly do you compute logic using water?
Well, the answer is a mind-bending invention called the polysynapse hydraulophone. It looks like a fountain, but it's actually a highly complex musical instrument where blocking specific water jets acts as a multi-level fluid logic processor.
Here's how the computation plays out. The interface is a row of continuous water jets. When you touch or block those jets with your fingers, you're diverting the flow. Deep inside the instrument, these flows crash together in complex pipe networks called synapses. These synapses use the natural resistance and inertia of the water to mix the flow in highly specific, mathematical ratios, sending perfectly tuned pressure into sounding chambers. Because you're playing with an actual fluid, you unlock what's called polyphonic embouchure. That means you get total, continuous, real-time control over the pitch, volume, and timbre of every single note, all at once, just by changing how you squish the water.
Which leads us directly to the mathematical concept that makes this whole thing so incredibly expressive. Think about a normal computer keyboard. You click a key, it's a binary 1 or 0, on or off. But this fluid system measures something called absment. Absment is the time integral of displacement. To put that into plain terms, it doesn't just measure how far your finger pushes into the water jet, it actively measures how long you hold it there. It turns the raw flow of water into a prolonged, deeply expressive mathematical variable. It's a level of user interface richness that solid-state electronics frankly struggle to match.
Section 5. Supercritical CO2 microstructures. Bypassing boundaries.
Okay, let's plunge into an extreme thermodynamic state where the actual physical boundary between a liquid and a gas just completely ceases to exist. It sounds like science fiction, but it's very real. If you take something common, like carbon dioxide, compress the heck out of it, and heat it past its critical point, it turns into a supercritical fluid. These things are absolute thermodynamic unicorns. As you can see, they maintain the heavy, solvent-like crushing density of a liquid, but they also possess the rapid diffusivity and super low viscosity of a gas. So they can permeate into tiny spaces just like a gas, but they dissolve materials exactly like a heavy liquid. This weird duality solves a massive engineering headache, drying ultra-delicate materials. Imagine you have an aerogel, which is basically a sponge made mostly of air, and it's incredibly fragile. If you try to dry it with a normal liquid solvent, the liquid's surface tension actually drags and pulls on the microscopic structures as it evaporates, totally crushing them. But a supercritical fluid? It has absolutely zero surface tension because there's no boundary between liquid and gas. So engineers use it to whisk away solvents without causing any structural collapse. The supercritical fluid just quietly phases out, leaving these impossibly delicate, perfect nanostructures completely untouched. For our final act, Section 6, Liquid Gallium Synchrotron Cooling, Extreme Engineering. We are now pushing into the absolute extremes of engineering to cool quantum-level optics. Inside next-generation X-ray facilities, incredibly delicate silicon crystals are getting hammered by intense beams, creating thermal loads up to 20 kilowatts. That's a huge amount of heat. Normally, you'd use water to cool things down, but you'd have to pump it so fast that the turbulent flow would physically vibrate the optics, ruining the precision of your photon beam. The fix? Liquid gallium. It's a dense, heavy metal with incredible thermal conductivity. You can pump liquid gallium at a slow, lazy, vibration-free pace, and it will still pull enough heat away to keep your X-ray beamline flawlessly stable and chilled. But wait, it gets better. This leads to what I think is the ultimate engineering hack. Synchrotrons have to operate in intense, high-vacuum environments. If a normal water cooling system gets a tiny micro-leak, that liquid instantly flashes into vapor and totally ruins the vacuum. Liquid gallium, however, has an impossibly low vapor pressure. So if a micro-leak happens, it doesn't vaporize at all. Instead, it just sits there and slowly reacts with whatever stray oxygen is floating around. It acts exactly like a chemical sponge, a getter pump, meaning a leak literally purifies and improves your vacuum. No way, right? And what if you have a catastrophic spill of this stuff? You'd think you'd need a specialized hazmat crew in there for a week. Nope. Pure liquid gallium can be frozen into a solid chunk just by pouring some cold water right over it. Then you just pick it up like a heavy rock. It's a beautifully simple cleanup trick, and it perfectly captures this elegant juxtaposition we've been looking at today, taking these incredibly intense, high-tech quantum problems and solving them using the raw, fundamental properties of fluids. We have covered some serious ground in this explainer. We started with the 17th century physics of Pascal's force multiplication, ventured into autonomous space actuators and smart magnetic damping, explored musical fluid logic, and went all the way to the absolute bleeding edge of quantum light with supercritical structures and liquid metal cooling. If there's one thing we've proven, it's that fluids are far, far more than just passive industrial tools. They are dynamic, they are highly tunable, they are the ultimate adaptive interfaces of tomorrow. So the next time you pour yourself a glass of water, I want you to really think about it. What invisible power is that fluid hiding, and what else could fluids be secretly powering in our future? Thanks so much for hanging out with me on this explainer, and remember to keep questioning the physical world around you.